Welcome back to the fourth lecture of the course, Collaborative Robots, Theory and Practice. So in this lecture, I'll discuss mathematical Jacobian, what is the definition of a Jacobian, the robot Jacobian, velocity analysis, how to compute a general Jacobian, Jacobian inverse, how to do that, singularity and degeneracy, what it is, singularities of a standard serial arm, which is a 6 degrees of freedom, industrial cobot or a robot, will do acceleration analysis as well. So let us begin. So what exactly is a Jacobian? Why we are talking about that here? Because Jacobian relates two different rates. Let us say you have y, which is a function of x1, x2, x3, x4 and xj. So these are all the input variables on which the output variable, that is y, depends on. Okay. So this may be expressed like these. Okay, delta y is equal to del f by del x1 delta x1 del f by del x2 delta x2 plus so and so till this. And similarly, if there are multiple outputs which are related to same inputs, that is x1, x2, x3, x4 and so on, so they all can be written like this. Okay, if I pack them together in the matrix form, so all the output variables are here, all the input variables are here. This is what is the matrix of partial differentials of f, which relates the input to the output, basically input rates to the output rates. So it relates two different rates. So in case of robots, when you have end effector position, which is a function of input joint angles, so end effector pose of the robot depends on theta 1, theta 2, theta 3 and theta 6 in case of 6 degrees of freedom robot, or it can be 7 degrees of freedom robot. In that case it will be up to theta 7. So in that case, end effector rate mean angular velocities of the end effector and linear velocities of the end effector, that is related using a 6 cross n Jacobian, where n is the degrees of freedom of the robot, where theta 1, theta 2, theta 3, theta 4 and up to theta n are the input joint variables. So joint variables can be in terms of rotary joint variable or prismatic joint variables. Okay. So where omega x, omega y, omega z represents the angular velocity of the end effector about x, y and z axis about the reference frame of the robot, and Vx, Vy, Vz are the linear velocity along the robot base coordinate axis. Okay. So this is written as twist. Twist is a vector which is a column vector of this. So this is twist vector of 6 cross 1 dimension, and Jacobian here would be of 6 cross n dimension, that is the Jacobian matrix which relates the output rates to the input rates. So and this is the joint variable, so that is theta n cross 1. So this is how Jacobian is defined for a general robot of n degrees of freedom. Okay. So now let us calculate Jacobian for a 2 degrees of freedom planar arm. Okay, this is one of the very simplest arm which can be derived by hand calculation also. So we'll see that now. So A1 and A2 are the link lengths, theta 1 and theta 2 are the joint angles, x and y are the end effector coordinates. Okay. So now x and y can be written using forward kinematics. It can be evaluated here also by taking simple projection. So this is A1 C1, A2 C12, A1 S1, A2 S12. So sum of these two will be x and y. Okay. So this is forward kinematics. So if I take differential of this, so taking derivative on both sides will give me this. If I expand that, I'll get this. Okay, expanding these. Okay, psi S12 here I would mean sine theta 1 plus theta 2. Okay, similarly for cos 1 2, and S1 would mean sine of theta 1. Okay. So, if I rearrange them in the matrix form, it comes to x dot y dot is equal to 2 cross 2 matrix into theta 1 dot theta 2 dot. Theta 1 dot and theta 2 dot are angular velocities of the joint rates, and x dot y dot is basically the end effector linear velocities. In case of a 2R manipulator, it can only move in two linear directions. Okay. So, this is your x dot direction, this is your y dot direction. Okay. This cannot rotate because you do not have that degrees of freedom in this type of robot. Okay. So, what is this basically? So, this is the Jacobian. So, you see now it is relating the differential motion of the joints, that is this, to differential motion of the end effector. Okay. And the term which is here is actually the 2 cross 2 matrix, which is nothing but a Jacobian which relates the joint rates to the end effector rates. Okay. Okay, let us do velocity analysis now. So, link velocities first. So, position vector of the joint frame. So, let us say this is a link I of link length AI that terminates with joint I plus 1 and begins with OI frame, and before to that you have link I minus 1 that begins with OI minus 1 frame. Okay, and link length vector here is AI minus 1. So, this is the configuration of two consecutive link which are attached and floating in space as it is shown. Okay. OI vector is the position vector of OI frame, OI minus 1 vector is the position vector of OI minus 1th frame, okay, with respect to the base frame which is O, which is shown here, that is the fixed frame. Okay. So, the position vector of the joint frame is given as OI will be equal to OI minus 1 plus link length vector. So, if I can draw it here, so OI is equal to OI minus 1 plus this vector, that is using vector triangle. You can quickly obtain it, you can write it like that. So, taking derivative of this, what do I get? Y dot is equal to yi minus 1 dot plus ai minus 1 dot. Okay. So, what are these terms? If you can see it closely, so how much is ai minus 1 dot? Let us isolate this link here. So, if this is ai minus 1, so it is rotating about this joint by an angular velocity omega I minus 1. So, what is the velocity that is associated with it? It is the velocity along this direction. Okay. That is because of joint velocity of this frame OI minus 1 at this frame. Okay. So, it rotates like this and it creates a velocity like this. Okay. So, that is in tangential direction. So, this is AI minus 1 dot. Okay. So, because this is not a prismatic joint, so it will not go along this direction. So, that is the velocity associated with this, and angular velocity omega I will be omega I, that is the angular velocity over here, will be equal to angular velocity up till here plus angular velocity of this joint. So, this is the joint angular velocity, that is angular velocity of I with reference to I minus 1, and omega I is the angular velocity of frame OI minus 1 till here and this. So, this can be written as this. So, now if I put them in the revolute joint, so it comes out to be this. So, omega I is equal to, it is exactly this equation, omega I minus 1. So, this is the joint rate, this is the magnitude of the joint rate, and this is the direction which is along the axis of rotation. Okay. So, this is equal to this, and now this equation is written here as, just I have substituted this to this and it comes out to be this. This is for revolute joint. In case of prismatic joint, because the joint itself does not have any angular velocity, so next link velocity is exactly equal to previous link velocity, angular velocity, and now you have linear velocity is because of three different components. First one is linear velocity over here, and linear velocity due to the rotation of this link, okay, and linear velocity because of expansion of the joint, okay. So that is due to the expansion of di, okay. So that is always there. In this case, you see, because there is no, this is frozen, okay. So whatever is the angular velocity of this becomes angular velocity of this link as well, but this is expanding also. So if this is expanding, so you get what? Now you have di dot, that is the rate of change of displacement along the direction of motion. Direction of motion is given by ei. This is in case of prismatic joint, okay. So these are the link velocities. Let us see if we can calculate Jacobian using the vector matrix approach for a general n degrees of freedom serial robot, okay. Moving on with the similar analogy, the way we did it here, okay. Omega 0 angular velocity. So this is the structure of this robot, a general robot. This is link 1 attached to the frame 1 and it is attached to the ground. This is next link, okay. This is the next velocity, angular velocity at the joint, next joint, next link, next joint, next link, so on so forth till it terminates at the end effector, which is here, okay. So omega 0, because it is attached to the ground, it is equal to 0. How much is omega 1? Omega 1 is equal to theta 1 dot, that is the magnitude, and along the axis vector, okay. So this is your omega 1. Similarly, omega 2 will be equal to omega 1 plus angular velocity of the joint 2, this is the magnitude, and axis vector 2. So that is how it will propagate, and finally omega n will be equal to this. So this is quite trivial for angular velocity case. For linear velocity, so what you see here is angular velocity at nth link will be equal to angular velocities of all the joints prior to I. If it is for I angular velocity, so it is due to the angular velocity of all the links that comes prior to this, okay. Okay, now the linear velocity. In case again you see ground, because it is attached to the ground, the first linear velocity would become equal to 0. Next linear velocity will be equal to first linear velocity and linear velocity due to the angular velocity of the first link, okay. So that creates a tangential linear velocity, okay, that is here, and if I can club it together, it is omega cross r. So this is omega, this is radius, so this is this distance, okay, omega cross r. And in case this continues further, okay, so it goes like this. So final omega n would be equal to this, and what is this actually? It is velocity contributions due to all the joint motion prior to the nth joint. Let us say you are at a nth joint, okay, that is at the, that is over here, okay. So whatever is the linear velocity over here, it is because of, you see, because of rotation of all the links prior to this. So because of this angular velocity over here, because of this angular velocity over here, okay, and because of all the links which are here. So contribution of all the angular velocity and the distance. So angular velocity here and the distance from 2 to n, okay. In this case it is 2, so it is 2 to n, omega 2, 2 to n, so on so forth. So for all of them it will be added together and it will have multiple linear velocities, and all will be added to get the final linear velocity, okay. So Aij is basically is this, I to j is this, and these are the notations that I have used here. Okay. Similarly, the end effector is a part of the last link. So, this is the part of the last link basically. Let us just evaluate the term which comes here, because this was quite easy, this is quite trivial. Now this one, so O3 dot will be equal to O2 plus omega 2 A2. So how much is omega 2? Omega 2 can be substituted directly here. Okay. If I put that here, that is from here I have copied it. So this omega 2 comes here and you expand it and you can derive it till here. So A2 3, that is from 2 to 3, frame 2 to frame 3. Okay, so this is how it is. If it is 3, it is 1 to 3 and 2 to 3. Okay, and these are the theta 1 dot and theta 2 dots. So this is how you keep doing, and finally for the n link it is like this. So now these are the two equations that we have obtained. This one is for angular velocity, this is for linear velocity. If I pack them together again, so these two comes here and you have theta 1 dot, theta 2 dot, theta n dot. So all are arranged here, extracting from all the terms, and this becomes your robot Jacobian. It is, the dimension of this would be E here is 1, 2, 3, and again this is a vector 2, 3. So total 6 cross n, this is n cross 1, this is 6 cross 1. So this is how, these are the dimensions, and here is your robot Jacobian. It comprises of all axis vectors and the distance vectors from the link I to end effector, I to end effector. Okay, likewise. Okay, so this is your Jacobian, and it has basically two components, j omega and jv. This is responsible for linear velocity. The upper row is responsible for angular velocity. Got it? So the column of j in case of revolute joint, it is like this. In case of prismatic joint, the velocity vector would be, because there is no angular velocity, this goes to 0, and you have linear velocity same as that of the previous link. So that makes this as EI. Okay. So now let us use this and see if we can do it for a 2R planar arm using the general Jacobian matrix, not taking the differential. Okay. So simplified expression could be, because it can only have linear velocities, it has no control over angular velocities. So we'll consider just the JV component of the Jacobian. So that is EI, AI, E type. Okay. So E1 and E2, that is the axis vector, will be along z axis only, because you know all the joint axes are along z axis. Okay, so that is over here, it is perpendicular to the plane of this paper. So z is out of the plane of this. So you have z1, you have z2, both are here. So that is here. So they can be written as E1 is equal to E2 is equal to 0, 0, 1. They are unit vectors, so it is 1. So I have transposed it to make it compact, but actually it is like this. So these are the z axis, and then A1E, that is frame 1 to end effector, from 1 to end effector. So that is equal to A1 vector plus A2 vector. Okay, and that can be quickly written as this. This is using trigonometric projection, you can write it. Okay, so it is basically, it is this and this. This is first component, this is second component. Okay, and along z it is equal to 0. So this is A1E. Similarly, A2E, from 2 to end effector is A2 vector, and that can quickly be written as this and this. So this over here, this over here, z is becomes equal to 0. Okay. Now taking the product, so E2 A2E will be equal to ijk, you know how to take cross product of this. So component will go like this. So E comes from here, and from here you take 2E, it comes out to be this. And similarly E1 A1E cross product would take you to this. Again you take the first value from here and A1E from here, and you take cross product, you get to this. Okay. Now if I arrange it, extracting the non-zero terms of J and arranging in 2 cross 2 matrix, I get exactly the same Jacobian the way we derived it earlier in a 2 cross 2 matrix we have derived using simple taking derivatives of the positions. Okay. So it comes out to be the same. So this you remember, because it is a planar system and it does not allow any rotations, we have taken it like this. Otherwise we would have taken also the EI component, okay, E1 and E2 component. So now can we extract all these parameters that I have used, E1, A1E, A2E, using a general homogeneous transformation matrices? So that is what we will try it out here. So extract the kinematic parameters from homogeneous transformation matrix. So Ti is equal to, you know, it is A1. Whenever I write 1, it is with respect to 0, 2 with respect to 1. So if it is with respect to I, it is respect to I minus 1. Got it? Okay. So this is what is here. Okay, it is, you know, all the products will finally give you the final homogeneous transformation matrix. Got it? So now T1 is equal to this, T2 will be equal to till A1 and A2, T3 and so on and so forth. You do this. So this is the overall forward kinematic transformation. These will take you to the frame which is just one prior to the sixth one, that is for the fifth frame, this is for fourth frame, this is for third frame, likewise. Okay. So now the last column EI, the column which is here, are z axis vector. You know the component of z along x, along y, along z lies here. So this essentially is nothing but the axis vector. Okay, axis vector. So that is can be extracted from all of this. So if it is for first axis, you have to use this. For second axis vector, third axis vector, fourth, fifth and sixth axis vector, for all the consecutive TIs, this column, the third column, first 3 rows will give you the axis vectors. Okay. Now this is the final term. You know you have to find out AIEs also. So that can be obtained from the position vector. So that also is available here. You see, this is the position vector of any ith frame with respect to the O. Okay, that is the fixed frame. Okay, so I'll use that here. Okay, so A1E, A2E will basically will be, so let us say I want to find out AIE. Okay, this vector. Okay, so how will I do it? I'll simply use this vector and this vector. Okay, this is nothing but the end effector vector. Okay, this is obtained from all the AIs which are here, from here to here. Okay, if I take product of this, whatever I get, the homogeneous transformation matrix for this joint OI, from there I can extract this one. So using this vector triangle I get this. Okay, for all the links I can do in a similar way. So all the AIEs can be obtained. Now this we have already seen. Okay, now we'll put them in place in this matrix. Okay, whatever we have extracted, EI is an AIE, and similarly the cross products are put over here. Okay, this is the way you can extract all the homogeneous transformation matrix elements and use them to calculate Jacobian. Got it? So finding out the inverse is again very trivial. Okay, you already know twist is given as Jacobian into theta dot. Okay, so if I take inverse, it should give me this. This is very trivial, provided this is a invertible matrix, that is a square matrix only. So in order to find the joint rates, basically what we, in quite a lot of applications like welding, adhesive dispensing, profile following maybe, okay, or if it is a painting, you already have an input of end effector velocity and you have to find the joint velocities, okay, corresponding joint velocities, okay, for the given end effector velocities. So how will you do it? All these applications will demand this particular equation, okay. So their Jacobian inverse will be required. Is it always possible? You know, it is not possible because it may or may not be a square matrix, okay. So alternative approach would be, if this is the equation, you know, multiply both sides of it by Jacobian transpose, so you get to this, okay, this over here and this side is here, okay. Now J transpose J is a n cross n matrix. So if you take product, it becomes a square matrix, okay. Now this is invertible. So theta dot now can be, by taking this as inverse to the other side, now this is here Jacobian transpose TE, and this term is known as pseudo inverse, okay. It is also known as Murray-Penrose inverse. This is quite easily possible in case of a 7-DOF robot. You can use this approach where you have n not equal to 6, okay. In that case you can use this to take the inverse, okay. There are limitations to this also, we will talk about this later, okay. This is how you find out the Jacobian inverse. Now there are few terms which are very important here. One of them is degeneracy, that occurs when robot loses a degrees of freedom and thus cannot perform as desired. So what are those conditions? Okay, the first one is the robot joint reach to its physical limit and thus cannot move further. Okay, there may be some joint limitation because of the motor fixture, the architecture of the system, okay, or because of the joint limits, motor limits, okay. So it cannot go further and it cannot perform. If it is expected to go fully stressed condition, but because of the architecture, let us say it cannot move, so that is a physical limit, okay. So and it cannot move further, and that is leading to this condition again. Okay, now second one is robot reaches the workspace boundary beyond which it cannot go, okay. So those are the conditions where your robot can go degenerate. Next one is in the middle of the workspace, if z axis of two similar joints becomes collinear, okay, moving any of the joint would result in the same motion. So that is the case when it is again degenerate, okay. So if degrees of freedom is less than 6, as in case of Iscara robot, it cannot roll, it cannot pitch. So there is no solution for the robot along those directions, okay. So that is also a degenerate system. And when the determinant of Jacobian becomes equal to 0, okay. So as you have expected, twist is equal to j theta dot. If I have to find out theta dot, what we did, Jacobian inverse of twist of the end effector, that is what we know. So Jacobian inverse is basically adjoint of j by determinant of j. So if determinant of j becomes equal to 0, in that case what happens? This is not possible. So you cannot extract theta dot for the given end effector trajectory. So in that case, determinant becomes equal to 0 and you cannot calculate the joint rates, okay. So that is one of the important cases, because this is widely used in robot control also. So it is not always inverse kinematics approach we find out the joint angles, we also sometimes use to find out the joint rates using this approach. Okay. The mathematical condition which is responsible for this is known as singularity. Okay. So, basically determinant become equal to 0 is a singular case, mathematical singularity, and that is what is the case for point number 2, point number 3 and point number 5. So, determinant becoming equal to 0, or in the middle of the workspace if z axis of two similar joint becomes collinear, mathematically even the j becomes equal to 0. Okay, determinant of j also becomes equal to 0. The robot reaches to its boundary in quite a lot of cases. In those cases also determinant becomes equal to 0. Okay. So, now I will just show you a small video for UR robot which does have a singularity. The link to this video I have mentioned it here. This is wrist singularity. This is wrist singularity. You see, in between it became singular and robot halted for a moment, then it moved forward. It gets stuck. There is infinite solution for that particular pose, that is wrist singularity again. This is shoulder singularity. You saw in between it had infinite solution again. Got it? This is elbow singularity. It is in case of fully extended condition mostly. That is, robot reached to its boundary. Got it? So, these were the cases, singularity of a standard 6DOF industrial robot or a cobot. So, in case of UR, you saw these were a few. Okay, wrist singularity, axis 4 and axis 6. So, where are they? Axis 1, axis 2, 3, axis 4 and 6. Both are coincident. Okay, they are parallel to each other. Okay. In this case, elbow or a boundary singularity, you see this and this came in a straight line. Okay. So, wrist lies on the plane passing through the axis of joint 2 and joint 3. This is joint 2, joint 3, wrist lies on the same plane. Okay. So, that is a boundary singularity. It is also known as elbow singularity, and the final one is the shoulder singularity. Center of the wrist, okay, lies in a plane passing through the joint axis 1 and 2. Okay, so this is joint axis 1 and 2. So, it lies exactly above this. So, this is again a place when this whole of this robot can rotate about this axis, and that is a shoulder singularity. Okay, that is there in case of standard industrial robot or a cobot also. This is exactly having the same architecture as that of Fanuc 35IA that I have shown earlier. So, this is elbow singularity. You see this and this comes in a straight line now. Shoulder singularity, you have this axis getting aligned with the last axis, two axes, and wrist singularity here is this axis comes in line with the fourth one. Fourth and sixth gets in line. So, these are few singularities which are there. Okay. So, now singularity analysis of a 2R planar arm. Now that we already have this matrix in hand, I will just check if where does it go singular. Okay. The simplified expression for Jacobian of a 2R arm is this. So, determinant of this and equate it to 0, it gives me to this equation. If I solve it, what I get is this, and finally this leads to sine theta 2 equal to 0 or theta 2 is equal to 180 degree. So these are the two places where it is singular. Okay, so where are they? Theta 2 become equal to 0, that means this and the angle becomes equal to, so this is here, so whole of the robot goes to a straight line. Okay, straight linear. Okay, in that case it is boundary singularity, that is what is happening. And when it is infolded, theta 2 equal to 180 degree, it is fully infolded, the second link comes here, again it is singular. So these are the two physical conditions in which it is having singularity. It is not depending on theta 1, you see. So anywhere where it is finding the boundary, everywhere it is going singular. Okay, so these are the significance of these two solutions. Okay, so let us do acceleration analysis now. We have checked upon the velocity a lot. Okay, so how to find out the accelerations here? So this is what you already have in hand, that is twist is equal to Jacobian theta dot. Taking derivative of this would give, this is the acceleration, twist dot is equal to j theta double dot plus j dot theta dot. Okay, so what is twist dot? It is basically angular acceleration and linear accelerations of the end effector. Theta double dot is the joint acceleration, that is here. Jacobian is Jacobian, you already know it. Okay, Jacobian dot can be evaluated using, you already know Jacobian is equal to EI cross AIE. So this is what are the various columns of Jacobian. Okay, so if you take derivative, ith column will be equal to this. So first into derivative of second plus second into derivative of first. So that is the way you know derivatives are taken. So it is just written like this. So this becomes ji dot, that is substituted here. Theta dot is angular velocity of the joint, theta double dot angular acceleration of the joint, j is Jacobian, j dot is found out like this. That is how you find out the end effector accelerations, angular and linear. Okay. Okay, can you try finding out j dot for a simple two link arm? Now I want you all to do this exercise as a homework. So just twist Jacobian times of theta dot, do it for a 2R planar manipulator. We already have Jacobian in hand for that. I would like you to do it. Okay, that's all for this lecture. So in the next lecture we'll do inverse kinematics of 7 degrees of freedom KUKA LBR IVA robot. We'll discuss what is null space also. That's all. Thanks a lot.